Hello all and welcome again to this online course on fundamentals of composites and cellular materials. So, we are talking about interface for last couple of classes. We discussed the basics of interface, what are the different factors which controls the interface. We talked about wettability, we talked about the factors which again affects wettability in terms of roughness, chemical reaction, atomic structure. We also discussed about interfacial bonding. So, in the last class I just introduced about the interfacial bonding, the various kinds of interfacial bonding. So, I have a plan to go on that particular topic to provide you some more information on interfacial bonding, some more details of interfacial bonding, the different kinds of interfacial bonding. And then the final thing which I would like to discuss here is how do we measure interfacial strength. Okay. So, we will see how much we can cover in today's class, or else we will move to the next class also. So, let us begin. So, in the last class I showed you this particular schematic where the different kind of bondings are shown, the different mechanisms of bondings are shown. For example, A and B, in case of A we are seeing molecular entanglement, and the second case we are seeing electrostatic attraction between two surfaces. So, this kind of bondings can be classified as physical bonding, right. Similarly, when there is some kind of chemical reaction or chemical diffusion is taking place, dissolution is taking place between atoms, that comes under chemical bonding. For example, in this particular case, two groups of atoms, two groups of molecules are actually reacting at the interface. In case of polymer materials. Similarly, here we are seeing atomic diffusion or atomic dissolution taking place between the two phases, and in this particular case we are seeing that ultimately there is some kind of chemical reaction at the interface taking place, and all this falls under the category of chemical bonding. And finally, we have mechanical bonding also, where there is no chemical bonding, no chemical dissolution, or no physical bonding as well could be, but just only mechanical bonding. So, we will discuss about this different kind of bondings in little bit more details in the next few minutes. So, yes, we discussed that the major type of interfacial bondings are mechanical bonding, physical bonding and chemical bonding. So, let us talk about mechanical bonding initially. Now, mechanical bonding is what? Mechanical bonding is basically mechanical keying or interlocking between two surfaces, which can lead to a considerable degree of bonding. Now, how it happens? If you look at this particular schematic, we can see that in between these two surfaces there is roughness, and now as let us say one is matrix, other one is fiber. So, the matrix is let us say getting solidified on this surface of the fiber. So, because of this solidification shrinkage, there will be a radial gripping stress, which will be acting radially. The stress will be acting radially on the surface of the fiber, right. And because of that, there will be an interfacial stress, or we are calling is at as interfacial shear stress tau I, and this tau I is given by tau I equals to mu multiplied by the radial stress. Now, what is mu? Mu is the coefficient of friction. Okay. So, what is coefficient of friction, or how that can be dictated? Okay. So, there are few factors which actually controls the mechanical bond. So, ultimately you can see here the mechanical bonding, or this tau I in this case, okay, this interfacial strength here, or interfacial stress because of mechanical bonding depends on these two factors. One is the radial stress and other one is the mu, or the coefficient of friction. Now, how can we have radial stress? Radial stress can act if there is mismatch in thermal expansion coefficient of thermal expansion. So, if there is CTE mismatch, and obviously there is CTE mismatch between fiber and reinforcement. So, because of that there will be radial stress, and had the radial stress, obviously as you can see the tau I value or the interfacial stress is higher. Similarly, by some means if we can increase the value of coefficient of friction mu, how can we increase that? Obviously by increasing the surface roughness, right. So, one factor we learned is that the mismatch of coefficient of thermal expansion or CTE mismatch leads to radial stress. Second point is the surface roughness. Higher the surface roughness, generally there will be coefficient of friction will be higher. Also, one more thing we should not forget is that during solidification, so when it is in molten state, obviously we do not have this kind of roughness, right, on the metal side. Okay. We have roughness on this fiber side. Now, the liquid molten metal, it will do based on its weightability, it will penetrate or it will enter inside the different level of crevices on this surface roughness, and once it gets solidified, okay, those will be acting as interlocking. Those solidified metals inside those crevices will act as the interlocking factors. Okay. So, there are three factors now we have learned. One is the radial stress, which is basically depending on the CTE mismatch. Second point is the mu, depends mostly on the surface roughness, and third point is again this mechanical interlocking because of the solidification, because of the molten metal penetrates inside the crevices, and that leads to this kind of mechanical interlocking. So, you can see here those points have been mentioned in different manner. So, radial shrinkage differences between fiber and matrix on cooling from a high temperature. I talked about difference in CTE that leads to radial shrinkage. Okay. Then matrix penetration that penetrating the crevices on the fiber surface by liquid or viscous flow or higher temperature diffusion, and that leads to this kind of mechanical interlocking. And I also mentioned about the mu factor, which is actually surface roughness. Okay. So, because of all these factors, it looks like there is no chemical bonding, but then it is not only about chemical bonding. If we can engineer the surface so that we can have very good mechanical bonding, we can have very good bond strength. Okay. In most cases where chemical reaction is not possible or chemical reaction is not suggested, in some cases chemical reaction is not good, right, that leads to formation of different kind of pore phases or which could lead to some kind of hampering of the properties, okay, harmful phases. In those cases chemical reaction is not wanted. So, in those cases we completely rely on mechanical bonding, and mechanical bonding could be very high. Okay. So, what has been shown here is that one thing is very important here. Yes, we can have roughness, okay, but then we should avoid this kind of void formation, or as I mentioned earlier in the last class is that the weighting should be proper. Okay. So, few important characteristics of mechanical bonding is that strength of mechanical bond is obviously lower than chemical bond, no doubt about that, but then if we can have proper mechanical bonding, it could lead to very good interfacial strength as well, as I was mentioning few minutes back. Rough interface causes efficient load transfer between matrices and interfaces. I have mentioned it few times in my classes. So, I do not think I have to explain that. Mechanical bonding is efficient in load transfer when the applied force is parallel to the interface. That is another important factor. How the load is being applied, that is also important. Okay. Now, in this particular case, okay, the load is being applied in this direction or in this direction. Obviously, you can see here if the load is being applied parallel to the surface, okay, not perpendicular. In this case actually the mechanical bonding obviously would be better, no doubt about that. Okay. So, ultimately surface roughness contributes to mechanical bonding provided good wettability between matrix and reinforcement phase, that we should not forget. Yes, surface roughness is very good, but then it must have good wettability as well. All right. So, let us move on. Okay. So, the next one is chemical bonding, and in chemical bonding we would like to discuss about dissolution bonding. Now, chemical bonding involves atomic or molecular transport by diffusion processes. I mean, we all understand that part. Chemical bonding includes covalent, ionic and metallic bonding, and the bond energies are quite high depending upon what kind of bonding we have. Do we have dissolution bonding, do we have diffusion bonding, or we have some chemical reaction taking place, and that leads to chemical bonding. Based on these different kind of bondings, we can have varied range of bond energies. Okay. As I have mentioned already, chemical bondings are two kinds, dissolution bonding and reaction bonding. Okay. Now, in dissolution bonding, basically some kind of atomic diffusion takes place, no real chemical reaction, but atomic diffusion, interatomic diffusion between the two phases would take place. Okay. And it is crucial that the components come into intimate contact on an atomic scale. Yes, obviously that is extremely important, so that there is proper I was mentioning about wettability earlier also. So, that the surface coverage has to be very good. Once you have very good surface coverage, then diffusion process will be more efficient, and there will be more atomic dissolution or atomic diffusion, and the bonding would be better. Surface should be appropriately treated to remove any impurity. That is again an important factor. Yes, surface should be free from any contaminants. If there is any contamination on the surface, that would actually restrict the diffusion process. So, obviously the surface should be clean, free from contamination to have good dissolution bonding. Okay. Now, coming to reaction bonding. In reaction bonding, as we all understand, there will be reaction at the interface. As you can see here, this is metal matrix, this is your fiber, and in between that we have an interface, and this interface, as you can see here, there are three layers. The two outer layers are basically the atomic dissolution layer or diffusion layer, where we have solid solution formation. Okay. So, you can see here in these two layers there is no chemical reaction, which are adjacent to the metal and to the fiber, or to the matrix and the fiber. There is no chemical reaction in these two adjacent layers, but some kind of chemical diffusion has taken place, and then this chemical diffusion ultimately leads to some kind of chemical reaction, and this chemical reaction product forms at the central zone. Okay. So, you can see based on this particular kind of interface how the atomic concentration changes. You can see the matrix concentration, matrix atomic concentration is quite high at this particular interface between the diffusion layer and the matrix, and then it decreases, comes to a constant value, because now we have a chemical reaction product. Okay. So, it is a particular compound has formed. So, it is fixed. Similarly, same for the fiber atoms, they are also you can see it is fixed because of a particular product formation, particular compound formation, and then it changes, it decreases here and it increases in this side, because these are only diffusion layers. Okay. Examples have been shown. Metallic system, solid solution and intermetallic compound formation can occur at the interface, as I have shown here earlier. In case of polymer materials, polymer surfaces form a bond by diffusion of matrix molecules, forming tangled molecular bonds at the interface. So, diffusion layer will be there, and then ultimately there will be bond formation in this particular case. As you have seen earlier, if you remember, let me just go back. So, you can see here in this case that kind of thing has been shown. You can see here these are the diffusion bonds are taking place, and then ultimately the two molecules are actually chemically reacting to form a new bond. Okay. So, similarity can be seen here as well. Okay. So, let us move back to reaction bonding. We are talking about reaction bonding. Okay. So, ultimately you can see this kind of structure, concentration wise of the different concentration of the different elements from the metal and from the matrix and the fiber, this kind of interfacial structure would be observed when there is some kind of chemical reaction taking place at the interface. Very good. Now, once we learnt about this reaction bonding or different kind of interfacial bonding, we talked about mechanical interlocking or mechanical bonding, we talked about chemical dissolution, we are talking about reaction bonding. Okay. Now, let us see ultimately what is optimum or how do we attain optimum interfacial bonding. Okay. Now, so far from our discussion, we have learnt that we can have different kind of bondings. We can have very weak interface like van der Waals force or electrostatic bonding or molecular entanglement. These are weaker bonding. Or we can have extremely strong interface, okay, like stronger than reinforcement. In that case, what will be happening? Interface will not fail. As you can see here, it says interface has lowest strain to failure, and in that case there will be no fiber pull out. Okay. If there is no interfacial delamination, if there is no interfacial failure, that means the interface is so strong that there is no crack propagation through the interface. So, there will be no delamination. So, there will be no fiber pull out. So, in this case the interface is quite rigid, the interface is quite brittle, we can say. Okay. So, that hampers the fracture toughness, and when we call it as an optimum interfacial bond strength, when at the interface there will be multiple failure sites. That means, interface is quite strong. Okay. That is what we want, interface is strong, but then at application of higher load at multiple sites of the interface there will be failure, which will basically absorb the energy of loading. Okay. And because of that, the fracture toughness will improve, strength improves anyway because of high interfacial strength, but then the interfacial strength is such, it is optimum. So, it also allows some amount of interfacial delamination, and that improves fracture toughness. So, optimum case is that we should have high interfacial strength. Yes, we should have very high interfacial strength, but it should also allow interfacial delamination at particular stress level. Okay. Okay. So, now ultimately what we learned from here is that maximize the bond strength is not always the goal. The bond strength's nature varies based on requirement. This bond strength is different in MMC, it is different in CMC. Okay. As we have learned, in case of CMCs, we do not want a very strong interface. In case of MMC also, we want a very strong interface, but then the interface should not be brittle in nature. It should cause some amount of delamination at higher stress values to improve or to have higher fracture toughness along with high strength. Okay. Now, how do we obtain this optimum interfacial bond? How do we control this bonding? Okay. So, there are few ways to do that. See, in one case, in some cases I want very high interfacial strength, in some cases I want moderate interfacial strength. How do I take care of that? Yes, there are few factors which you can do. For example, we can treat the fiber or reinforcement surface physically or chemically. That means, we can have, obviously we can have roughness, we can control the level of roughness, we can have macro roughness, we can have micro roughness. So, we can have certain kind of surface area which would promote mechanical bonding as well as some kind of chemical bonding, or at least higher surface area, better load transfer. Plus, we can also treat the fiber surface or the reinforcement surface, so that promotes some kind of chemical bonding. Okay. In we can have like we can have a composite material, this is the matrix and let us say this is the reinforcement, and intrinsically they may not have any chemical reaction, but then on the top on the surface on the surface of the particles or the reinforcement, we can think about having a particular layer or coating of a phase which would lead to some kind of chemical reaction. Okay. So, this kind of engineering can be done. So, that is why treatment of fibers or reinforcement, and also we can modify the composition of the matrix itself. So, you can incorporate certain elements or certain phases which actually would promote chemical reaction at the interface. So, either way we can do, we can have a coating of a particular phase on the second phase or on the reinforcement, and that would promote chemical reaction, or in other way we can have certain elements or phases in the matrix itself, and that would lead some kind of chemical reaction at the interface. Ultimate goal is to promote some kind of chemical reaction. Okay. So, yes, we can have both. We can try to optimize the chemical reaction as well as, that means chemical bonding, as well as surface roughness, that means mechanical bonding. Both we can control to have an optimum level of interfacial bonding. And I will be talking about certain examples in next few classes, where we will discuss about this bond, how actually we can have different kind of interfaces, and that will lead to different kind of mechanical bonding and chemical bonding. Okay. For the time being, let us concentrate on something else, is that we have learnt about all this bonding and wettability and all those things. The point is that how do we measure this interfacial strength. So, now I will discuss about certain techniques by which we measure interfacial strength. Okay. So, let us move on. All right. The first test which I would like to mention here, it is quite old, and this technique was primarily being used for polymer matrix composites, but now it can be used for other matrix composites also, metal matrix composites also, which is called carved neck specimen test. Now, from the specimen shape, you can see why the name is this kind of carved neck specimen. What you see here is that this is the matrix material and a particular shape it has been made. You can see here the middle portion has it's carved like this, and then there is a single fiber which is placed or located centrally in this particular specimen. Okay. And the idea here is that a load will be applied. Okay. A load will be applied like this, and this load, because of this load, obviously you can see here because of this load, and what we understand is that the Poisson's ratio of these two material, the matrix and the reinforcement. Okay. So, the Poisson ratio of matrix and reinforcements are obviously different. So, based on this, actually this difference in Poisson's ratio and application of this particular load, which will be applying some kind of radial stress here, okay, the ultimate aim here is to cause some kind of delamination at the interface. Okay. Now, why carved? Because I want to have maximum stress in this zone. If I want to have maximum stress in that zone, obviously what I want here is that the area should be minimized. So, obviously with a particular load I will be having maximum stress at the central zone, and I will be seeing delamination at this zone only. Okay. That is the basic fundamental idea of this test. So, it says a special mold as a curved neck specimen of the matrix with a single fiber along the central axis. This shape maximizes the transverse tensile stress as I mentioned earlier. So, ultimately the transverse tensile stress and the different Poisson's ratio would lead to this kind of interfacial debonding, and so using this particular equation, okay, where sigma is the the load which is being applied at this particular surface particular area. So, we know the area here, from there we know the applied load. So, this sigma basically is equals to this sigma is equals to P by A, and this A is basically this area, okay. And then we know all the other values like the Poisson ratio, the EF, that is elastic modulus of the fiber, elastic modulus of the matrix. Okay. So, using this equation we can get the value of interfacial transverse tensile stress value. Okay. So, now the important factor here is that why I said earlier that it is basically used for polymers is that here actually you need to notice, or you need to know where exactly the failure is, when exactly the delamination is taking place, at what load the delamination is taking place, right. So, we need to know, we need to observe the delamination point. That is why earlier it was being applied only for transparent matrix, that means transparent polymer matrix. So, that I can observe when exactly or at what load exactly the delamination is taking place. So, I would actually monitor the surface, the interface here, and at a particular load I would be seeing delamination is taking place, okay, just by observation, and that load would be actually used as this sigma value to calculate the sigma value. Okay. But now obviously there are different advanced techniques. For example, we can think about having ultrasound testing or ultrasound monitoring, by which we will be able to notice any kind of delamination taking place even if we are not able to see it. Okay. So, now it is possible for not only for transparent matrix, but opaque matrix also it is possible now, this test. Another very important factor is that we also have to take care that this fiber is centrally located. Okay. So, that has to be taken care. So, you can see here there are certain factors which has to be maintained, or basically some precautions and limitations is that very precise alignment of the fiber along the central axis is required while doing the test. This technique was mainly for PMCs, as I mentioned earlier, less loading, need of visual delamination, all these things, transparent matrix, and loading requirement is also less when you have polymer matrix, but now this can be used for other opaque matrix as well. And now, as you can, I was talking about acoustic emission detection techniques could be used to avoid any kind of visual examination. Okay. So, in this particular class I have talked about the different kind of bondings, okay, and I have started talking about the different techniques by which we can measure interfacial strength. So, we will move on this particular topic only in the next class. Okay. We have learnt about the bonding in terms of three different kind of bondings. We have physical bonding, we have chemical bonding, and we have mechanical bonding. And we have learnt, or we have at least know what are the different ways through which we can optimize the bonding. We have also learnt that the requirement of bonding in different composite materials are different. So, we need to optimize the bonding. So, you have learnt about that in this particular class. And now we are learning about the different tests by which we can measure interfacial strength. The first one I have discussed in today's class is curved neck specimen test. Okay. We have some more tests coming in the next few classes, okay, and those I will be discussing as we move on, but today I would like to conclude today's class, and I would be also seeing you in the next class. So, thank you all.